Welcome back. Let's now start finding the actual partial derivatives for our gradient vector. The actual code that contains the example of training this network is accessible in my free Udemy tutorial, Vehicle Suspension Control 4, PID Tuning with AI, TD3. I included a short explanation of the code there as well. The link is in the description. Also, note that the free coupons that I offer for that, they have limitations in terms of time and the number of enrollments. However, don't worry, I will be renewing them periodically. Alright, we have 8 weights and 4 biases. It means that in total, we need to find 12 partial derivatives. In order to do that, chain rule in calculus is imperative. We are going to start from the back of the network and move towards the front in our differentiating effort. Once we've computed our outputs through forward pass, we can formulate the error function. We have our target outputs with a subscript t, and then the actual outputs that we got from the forward pass. And now, when we start moving backwards, then if you look at this network, you know that O1 star is a function of O1 because there is this activation function here in order to cross this blue line to get from O1 to O1 star. But then the variable O1, it itself depends on many other things. For instance, it depends on H1 star and also H2 star, because you can see that if you go backwards, then from O1 you can get to H1 star and also to H2 star. In other words, O1 is formulated by both H1 star and H2 star. And then of course it also depends on many other things like the weights and biases. I'm not going to be writing them all here. And then similarly, O2 star, which is this one here, it's a function of O2. When you apply the activation function to O2, you will get O2 star. But then you can see that O2 is also formulated by many other things like H1 star and H2 star, and then weights and biases. And then if we go even further, then H1 star is a function of H1, and H2 star is a function of H2, and then H1 and H2, they will also depend on the weights and biases and inputs. But let's start computing these partial derivatives systematically, step by step. First of all, I would like to know how this total error changes with respect to O1 star and O2 star. If you take this partial derivative, you will find that it's this one, and if you take this partial derivative, you will get this result. But this is of course not our final goal. We want to know how this total error changes with respect to the weights and biases. But in order to find that, we first have to know how it changes with respect to O1 and O2. In other words, I want to know this derivative, and I want to know this derivative. Now it's with respect to the outputs before the activation function. For that, I can use the chain rule from calculus. I have this derivative, which is this one here, times this derivative, which tells me how O1 star changes with respect to O1. And the reason why I have d here is because in the activation function that relates O1 to O1 star, I only have one independent variable here, O1. It's a single variable function. In that case, you use this notation with the d. You use the notation for partial derivatives when your function contains multiple variables, and then you have to specify with respect to which variable you're taking the derivative. And I will have the same thing here. I use this chain rule to compute this partial derivative. We already know these derivatives, which are these ones here. Now we also need these derivatives. So let's see. O1 star equals this activation function, and then O2 star equals this activation function. You can see that you only have one variable here, which is why we use d in this notation. If you take the derivatives of these functions, you will have this result here and this result here, and now you can very easily calculate the change of the total error with respect to O1 and O2. All you have to do is to multiply this result by this result here, and then this result by this result here. But of course, this is not our final goal either. We want to know how this total error changes with respect to these weights and biases here, W5, 6, 7, 8, and then B3 and B4. However, to find these changes, you would again use the chain rule. You already have these derivatives, which are this one here, and then you also have these derivatives, which is this one here, and so you're missing these partial derivatives. But remember that you computed O1 and O2 using these formulas in the forward pass, and from here you can very easily calculate these partial derivatives. This one will very simply be H1 star, this one is H2 star, then this is again H1 star and H2 star, and then this partial derivative here, and also this one here, they will both be 1. So once you have done your forward pass, you will have all these values that you had previously calculated them, and then you insert them here. Then the derivatives of the activation functions, you know their values as well, because from the forward pass you know what the values for O1 and O2 are, so you will have concrete numbers for these derivatives as well, and you also have concrete numbers for these differences. All that will enable you to calculate how the total error changes with respect to these 4 weights from 5 till 8 and these 2 biases B3 and B4. However, we also need to find how this total error changes with respect to the weights W1, 2, 3, and 4 and biases 1 and 2. So we have to go even more backwards. But here as well, we're going to be using the chain rule. So we want these 4 partial derivatives for the weights. If you look at the network, you can get them if you first figure out how it changes with respect to H1 star and H2 star. As you go backwards, then you figure out how H1 and H2 stars change with respect to H1 and H2 according to the activation function that governs their relationships, and then you figure out how H1 changes with respect to W1 and W2, because these are the weights that are connected to this neuron, and then you figure out how H2 changes with respect to W3 and W4. And then similarly, in order to figure out how error total changes with respect to the 2 biases, B1 and B2, you will again first need to figure out how the error changes with respect to H1 star and H2 star. Then you need these 2 derivatives, and then you need these derivatives. So with this chain rule, you can find the partial derivatives that you need. From forward pass, we already know that H1 was calculated like this, and H2 was this one. It's easy to see that this partial derivative is 1, and the same thing goes for this partial derivative. This one is I1, this one is I2, this one is again I1, and this one is I2. Next, we again used the sigmoid activation function in the hidden layer, which means that these derivatives here, they will be these ones, and you have all these values from the forward pass. You obviously have the values for the inputs, which are 0.1 and 0.2, then the derivatives with respect to these biases are simply 1, and then from the forward pass, you know the concrete values for H1 and H2 respectively, which you can insert into these derivatives, giving you concrete values for them, and that's how you will know this part, and also this part here. And what we need to do now, we need to figure out how this total error changes with respect to H1 star and H2 star. Once we know that, we know how the error changes with respect to the weights and biases, and then we can use that information to train our network. Now recall that our O1 star and O2 star, which both depended on H1 star and H2 star in both cases, because O1 star depends on O1, which in turn depends on H1 star and H2 star, and the same thing here, O2 star depends on O2, which in turn depends on H1 star and H2 star. So H1 star influences O1 and O2, and they influence the total error, and also H2 star influences O1 and O2, and both of them influence error total. However, we already have values for these partial derivatives. We calculated them right here. You needed these white derivatives here, and then these derivatives in cyan, and you would have the values for how the error changes with respect to O1 and O2 respectively. And the only thing that is missing now is these derivatives here, but remember that O1 and O2, they were calculated using these equations, and from here you can calculate these four derivatives. This one is W5, this one is W7, this one is W6, this one is W8. Note that in this gradient descent algorithm, the values for these weights, they are all at time k. These are the values that you used during forward pass. In our particular example, in the very first iteration, all these weights would have the values of 0.2, and you use them in the calculation of your gradient vector as well. And only once you have a complete gradient vector, then you apply this algorithm to update all the 8 weights and 4 biases at once. And so you now have the values for these two partial derivatives, which means that you have concrete values here and also here, which also means that you have all the partial derivatives that you need in order to fill in this gradient vector, and only once you have this gradient vector completely filled, that's when you apply this gradient descent algorithm and you calculate this new updated weight vector. You update all the weights and biases in your network. You will perform this forward pass again with the new weights. You will have a new error. You will compute the new partial derivatives, which means that you will have a new gradient vector. You update the weights again, and you do that thousands of times until your total error becomes very close to 0, which means that your real outputs will get very close to target outputs. And there you have it. You have the theory, and now to see how it is implemented in the code, enroll in my free Udemy tutorial, Vehicle Suspension Control 4, PID Tuning with AI, TD3. The link is in the description. Here on YouTube, however, we're going to continue with Q learning starting from the next video. Thank you.